Welcome. Today we're diving into nanogpt, a beautifully compact codebase from Andrej Karpathy. It's all about training GPT-style language models with maximum clarity and minimal complexity. So what does nanogpt actually do? It's designed to be the simplest possible GPT training system that still runs fast. You can train models from scratch on your own data, or fine-tune OpenAI's GPT-2 checkpoints. The entire codebase is built for readability. Everything you need lives in a handful of Python scripts you can understand in one sitting. And despite that simplicity, it scales from a single GPU all the way up to distributed training across multiple machines. Let's look at what this project is built on. The core is PyTorch, which handles all the model building and training. For tokenization, it uses TikToken, OpenAI's fast tokenizer. The Hugging Face Transformers library is here to load pre-trained GPT-2 checkpoints when you want to fine-tune. For data, there's the Hugging Face Datasets library to grab open web text, and NumPy for efficient binary file handling. And if you want to track your experiments, there's optional weights and biases integration. Here's how the repository is laid out. At the top level, you've got 3 core scripts. Model.py defines the entire GPT architecture in just 330 lines. Train.py is your training loop with distributed support. Sample.py handles text generation. There's a config folder with presets for different training scenarios, and a data folder with 3 example datasets. Character-level Shakespeare for quick experiments, BPE tokenized Shakespeare for fine-tuning, and the massive open web text dataset for reproducing GPT-2 from scratch. Let's zoom out and see how the pieces connect. First, you run a data preparation script that tokenizes your text and saves it as binary files. Then the training script loads that data, pulls in configuration parameters, and feeds batches through the GPT model. As training progresses, it saves checkpoints containing the learned weights. Later, you can load those checkpoints with the sample script to generate new text. The configurator sits alongside everything, letting you override training parameters without touching the code. Now let's talk about the model itself. At the heart is the GPT architecture, a stack of identical transformer blocks. Each block has 2 key components: causal self-attention, where each token looks back at all previous tokens to gather context, and an MLP layer that expands the representation by 4 times, transforms it, then compresses it back. Everything is wired together with residual connections and layer normalization to help the gradients flow during training. At the bottom, token and position embeddings convert discrete tokens into continuous vectors. At the top, a language modeling head turns the final representation back into a probability distribution over the vocabulary. Here's how a training iteration works. The data loader samples a random block of context from the memory-mapped binary file. The training script feeds that batch through the model in a forward pass, getting back logits and a cross-entropy loss. Then we run a backward pass to compute gradients. The training script accumulates gradients over multiple micro-batches to simulate larger batch sizes, then passes them to the AtomW optimizer, which updates the model weights. Periodically, we evaluate on the validation set to track how well the model generalizes. nanogpt supports 2 distinct workflows. On the left, training from scratch. You start with random weights and train on massive datasets like open web text, 9 billion tokens. This takes days on a cluster of GPUs, but you get a model that understands general language patterns. On the right, fine-tuning. You start with one of OpenAI's pre-trained GPT-2 models and train briefly on your custom dataset with a gentle learning rate. This is perfect when you want to adapt a model to a specific writing style or domain, and it only takes minutes to hours. Let's trace how text becomes training data. You start with raw text, novels, articles, whatever you want the model to learn from. The tokenizer, using GPT-2's BPE encoding, converts that text into a sequence of integer tokens. Those tokens are written to a binary file that can be gigabytes in size. The clever part is that this file is memory mapped, meaning we don't load it all into RAM. During training, we just read random context windows from disk on the fly, which is surprisingly fast and lets you train on datasets that are way larger than your memory. When you generate text, the process is beautifully simple. Start by encoding your prompt into tokens. Feed those tokens through the model to get predictions for the next token. Sample from those predictions. You can control randomness with temperature and limit choices with top K filtering. Append that new token to your sequence and repeat. This autoregressive loop continues until you've generated the desired length. Finally, decode the tokens back into readable text. The whole process happens in sample.py, which is under 100 lines of code. nanogpt connects to a few external services, all in straightforward ways. It pulls pre-trained GPT-2 weights from Hugging Face transformers. No authentication needed, they're public. It can download the open web text dataset through Hugging Face datasets, again public and credential-free. If you want experiment tracking, you can optionally log to weights and biases, which requires an API key but is disabled by default. And for distributed training, it uses PyTorch's DDP, the Distributed Data Parallel System, which just needs network configuration for multi-node setups. Let's walk through a typical learning journey. Imagine you're a student trying to understand how GPT models work. You start by running the Shakespeare character level preparation script, which downloads the tiny Shakespeare corpus and builds a simple character to integer mapping. Then you launch training with the provided config, a small 6-layer model. On a single GPU, this finishes in about 3 minutes. While it trains, you can read the entire model definition in model.py, all 330 lines, and actually understand how tokens flow through embeddings, attention, and the language head. At the end, you generate some amusing if imperfect Shakespearean text. Here's a helpful analogy for distributed training. Think of it like having multiple chefs cooking the same recipe simultaneously in different kitchens. Each chef, or GPU, has their own copy of the ingredients, which are the model weights. They each cook different dishes, processing different data batches. After each round of cooking, the chefs share notes about what worked and what didn't. Those are the synchronized gradients. Then everyone adjusts their technique identically. This parallelism means you can process 8 times more data in the same amount of time, dramatically speeding up training. Here's a glimpse of the actual model code. This is the GPT class initialization. Notice how concise it is. Token embeddings, position embeddings, a dropout layer, then a list of transformer blocks, layer norm at the end, and finally the language modeling head. The entire architecture is defined in plain PyTorch with no hidden abstractions. When you want to modify something, say, change the attention mechanism or add a new layer type, you just edit this file directly. Let's check in on the community side of things. This repo is marked as maintained, with the last commit from Andre happening in November 2025, about 6 months ago. There's been one commit in the past year, and Andre is the sole contributor. Activity has been pretty quiet recently, with 0 commits in the last 90 days. This is actually pretty typical for educational projects that reach a stable state. The code works beautifully as is, and Andre has moved on to other things. The project serves its purpose as a clean reference implementation, and the community continues to learn from it even without active development. So why does nanogpt matter? It proves you don't need a massive framework to train state-of-the-art language models. The entire system fits in your head, 1,200 lines you can read in an afternoon. Yet it runs at production speed, using PyTorch 2.0 feed-s compile feature and flash attention for efficiency. When you want to experiment, you're not fighting abstractions. You just edit the code directly. It's educational gold for anyone learning about transformers. And it's battle-tested, successfully reproducing GPT-2's validation loss on open web text. In short, it's minimalism done right.